Okay, hello everyone. Okay, okay. Who here has heard of sharding before? Who here is human? Okay. Wow. More people answered the first question than the second. That's interesting. Today I'll be basically making a presentation that's kind of similar to the one that I gave at EdCon, where I talked about what it's like to be a Casper FFG validator. Sorry in advance that the slides are half in Chinese. It's because I did this exact same thing in Beijing last week. But anyway, so the point of this is to look at what Casper and sharding is from the point of view of someone who is participating as a validator inside of a Casper and sharded Ethereum network. So let's suppose you just went to an exchange, you sold all your Tron, and you bought up 32 ETH. And you want to use that 32 ETH to become a validator and just participate in the proof of stake system. What do you do? So step one, deposit, right? So basically you deposit your 32 Ether, and you do that by sending a deposit transaction that includes, first of all, the 32 Ether, which is the size of a validator slot. Number two, public key. And notice I'm totally not specifying anything about signature algorithms here. Just try to think about this very generically for the moment. And number three, your withdrawal address. So the withdrawal address is where the money will go, plus rewards minus penalties when you're done staking it. So notice a few different things here, right? So first of all, the signing key and the key that controls the withdrawal address do not need to be the same key, right? So you can have one key that's for signing and one key that the money comes from, and you can have the money potentially just get sent back there when you're done. So this is designed that way because it gives you two very nice things. One of them is that if you want to, you can delegate signing rights. So you can basically delegate your validator slots and have someone else have the ability to sign on its behalf. And the other thing that you can do is you can stake in such a way that your signing key is an online hot wallet, but the funds are only withdrawable to a cold wallet. So you're staking with a cold wallet, but you still have the property that if that hot wallet gets hacked, you're generally not going to lose more than a fairly small fraction of the funds. So you send your deposit transaction. Step two is you wait to be inducted. Basically, you wait until the system kind of officially adds you as a validator. This may take up to 1 day, not yet determined. Who here is with me so far? Send a deposit transaction, wait. Okay. Step three, validate. So validate basically means, well, you're one of the validators. You are a proof of stake participant. Validators have two kind of primary functions. One of them is that they finalize the main chain. So this means basically the same thing that it meant to is they verify blocks on the shards. So verifying blocks on the shards basically means that they kind of both propose blocks for shards and also actually check blocks that other people have proposed. And if some set of blocks is approved, sharding validator related activity. So the distribution of responsibilities is kind of like this, right? So the main chain handles random number generation, which determines kind of proof of stake blocks, who gets to create main chain blocks, who gets to create shard blocks. The random number seeds are used to randomly sample committees of validators that needs to validate blocks on any particular shard. The main chain keeps track of all of the validators, keeps track of all of the validator slots, and it also keeps track of shards in the sense of keeping track of how many shards there are, when shards get added, when shards, when portions of shard chains get kind of confirmed into the main chain. So the main chain is this sort of manager shard that everyone has to kind of participate in and validate. The shard chains do the actual work that make the blockchain useful. So the shard chains process transactions and they store account and contract state, right? So validator assignment, right? So every epoch, where an epoch is expected to take maybe 1 hour, every validator is assigned to some newly selected random shard. During that epoch, the validator verifies and helps to confirm blocks that are on that shard. So you as a validator, you have some validator slot, and the system basically every epoch chooses for you. You go to shard 75 now, you go to shard 28 now, you go to shard 123 now. And when you're assigned to some shard, you are given the ability and the responsibility to participate in the block verification process that's happening on that particular shard. So the entire global set of validators is responsible for maintaining the beacon chain. Maintaining the shard chain is done by this pool of shard validators that gets very frequently reshuffled for each shard. Now, you might ask, well, what actually connects the two together, right? So, first of all, every shard block has to have a pointer to the main chain block that is in the same period as that shard block, and that is kind of the source of the randomness that determines which validator is allowed to create it. So that basically also at the same time creates a link where the shard chain can read the main chain. Now, how can the main chain read the shard chains? Well, this is done with crosslinks. So a crosslink consists of a set of about 100 signatures, could be more, number not exactly decided, some significant number of signatures. These signatures are from the validators that were assigned to a shard at some particular time. And this set of signatures basically can be included into the main chain, and they confirm a block in that shard into the main chain. So basically, the main chain maintains a database for each shard. What is the most recent crosslink from that shard that was submitted? And the way that that list changes is basically that this randomly selected subset of validators, what we call a committee, can submit a new crosslink, and that new crosslink basically has to specify, and the shard chain can generally happen more quickly, right? So blocks on shard chains can still have block times of like 5 to 10 seconds. So now it's called quadratic sharding because, well, basically, if the sort of implication here is that if you suppose one single computer can process roughly n transactions or kind of n objects, then the load of the beacon chain is going to be n. And the load of the beacon chain basically consists of, the largest portion of it is crosslink transactions, right? So the number of crosslinks that it can include, and so the number of shards that the system can manage is proportional to the load that we're willing to put onto a beacon chain node. Now, so that decides the number of shards. Now, on each shard, every individual block on each shard itself has a load of, or a validation load that's proportional to a node's computing power. And so the total capacity of a chain is proportional to the capacity of a node squared. Now, there are ways to do super quadratic sharding. There are potentially ways to do exponential sharding. We are not doing this at present, in part to just maintain simplicity, and in part because once you go super quadratic, there are kind of other bottlenecks that I'm not talking about here that we haven't really managed to make super linear, like validator size, like fraud-proof related denial of service attacks and so forth, that start to become much more tricky. And like basically, we do care about kind of preserving the integrity of the base layer, and it be basically at this point, that sort of stuff still feels too risky. Maybe when like fully working Starks for everything are working, it would be more appropriate to consider super quadratic sharding. We'll see. So crosslinks. So block proposal, right? So in addition to the process that assigns validators to shards for an hour at a time, there is a separate process which also assigns validators to shards for periods of 4 months at a time. And the purpose of this is that validators get randomly assigned to shards so that they can propose blocks. So why do you want to do this? Well, basically, the goal here is that we want proposing blocks on shards to be a process which just takes up a fairly, which for efficiency reasons is done by a smaller set of nodes that actually have to store the state of the shard, and we want to have some set of nodes that has some at least kind of partial guarantee of storing the shard's entire state. And like it is theoretically possible to go without this, but it does have like some fairly significant consequences to things like efficiency and particularly censorship resistance. So block proposers only have the ability to propose blocks, but block proposers do not have the ability to make crosslinks or perform the other kind of intermediate signatures that are involved in verifying blocks. So this is the full list of validator responsibilities. Number one, validate as in like verify the main chain, verify the beacon chain. Number two, every validator slot is validating 2 shards. Right? One of those shards is for block proposal, and one of those shards is for a block confirmation, and particularly making crosslinks that basically confirm the some amount of progress on the shard into the main chain. Propose blocks on shards. Right? Propose blocks on the main chain, and confirm shard blocks and make crosslinks. So these are the things that you do as a node in a sharded network. Right? Now, if this was, if we were to make this list for a regular network, there would basically be 2 items, right? One of those items is to validate the main chain, and another item is to propose blocks on the main chain. So the protocol does, the more ETH you have, if you want all of that ETH to be staking and earning staking rewards, the more validator slots you will be assigned to, and so the more things you will be assigned to validate at any one time, which means you will need more computing power. So this is one kind of pro-decentralization pressure, because it basically means that nodes that have smaller amounts of ether needs to only verify very small amounts of data. But if we're talking about like some big pool that's I don't know, like run by some big company that's validating with like 2 million ether, well, it's probably going to need to be validating the entire chain pretty much always. So like this is kind of a deliberate design decision to try to basically minimize the kind of unfairness between nodes that have differing amounts of ether. Rewards and penalties. So there are basically roughly 3 cases here. The first case is if you validate normally. So validate normally basically means you're validating, you're online, you're participating in all of your different responsibilities, and like everything is good. If more than 2/3 of the other validators also validate normally, you earn an interest rate. If this is not true, then you don't earn an interest rate, but you at least keep your money and you avoid penalties. Case 2, go offline. There's 2 cases here. One of those cases is if at least 2/3 of the other validators are validating normally, then you get only small penalties. The second case is that if you and more than 1/3 of the other validators are offline at the same time, then you suffer large penalties. And this is the quadratic leak mechanism. And if you want to find out more, just like look up those 2 words and there'll be like stuff talking about it. The third case is the worst kind of fault, which is where you sign invalid or contradictory messages. If this happens, then there's a penalty that you have to pay, that gets kind of automatically deducted, which is proportional to the percentage of other validators that also sign invalid or contradictory messages. So now the reason why we need to penalize this is because if at least 1/3 of validators do this, then the entire chain, basically that could potentially finalize contradictory blocks. If even like 2/3 of one committee is dishonest, then that committee can put a bad crosslink into the main chain. And if the bad crosslink actually gets into the main chain, then basically as soon as the fact that the crosslink is bad is detected across the network, the entire main chain after that point would have to be discarded. So basically, like signing anything that's invalid, going offline, any of these things, or not going offline, in this case, contradictory messages, are attributable faults, which means that if you commit the fault, you can have a proof that detects that you made the fault. And so this basically makes it easier to penalize those validators, encourage more sort of decentralized structures and topologies. step during this period, then you'll be able to recover your funds minus the penalties as calculated according to the partial slashing formulas. So that basically is how kind of Casper and sharded node validating works from the point of view of a validator. Thank you, and